JEP 441, Pattern Matching for Switch. Summary. Enhance the Java programming language with pattern matching for switch expressions and statements. Extending pattern matching to switch allows an expression to be tested against a number of patterns, each with a specific action, so that complex data-oriented queries can be expressed concisely and safely. History. This feature was originally proposed by JEP 406, JDK 17, and subsequently refined by JEPs 420, JDK 18, 427, JDK 19, and 433, JDK 20. It has co-evolved with the record patterns feature, JEP 440, with which it has considerable interaction. This JEP proposes to finalize the feature with further small refinements based upon continued experience and feedback. Apart from various editorial changes, the main changes from the previous JEP are to 1. Remove parenthesized patterns, since they did not have sufficient value, and 2. Allow qualified enum constants as case constants in switch expressions and statements. Goals. 1. Expand the expressiveness and applicability of switch expressions and statements by allowing patterns to appear in case labels. 2. Allow the historical null hostility of switch to be relaxed when desired. 3. Increase the safety of switch statements by requiring that pattern switch statements cover all possible input values. 4. Ensure that all existing switch expressions and statements continue to compile with no changes and execute with identical semantics. Motivation. In Java 16, JEP 394 extended the instance of operator to take a type pattern and perform pattern matching. This modest extension allows the familiar instance of and cast idiom to be simplified, making it both more concise and less error-prone. / prior to Java 16. If obj instance of string s equals string obj, use s. / as of Java 16. If obj instance of string s, use s. In the new code, obj matches the type pattern string s if, at runtime, the value of obj is an instance of string. If the pattern matches, then the instance of expression is true and the pattern variable s is initialized to the value of obj cast to string, which can then be used in the contained block. We often want to compare a variable such as obj against multiple alternatives. Java supports multi-way comparisons with switch statements and, since Java 14, switch expressions, JEP 361, but unfortunately switch is very limited. We can only switch on values of a few types, integral primitive types, excluding long, their corresponding boxed forms, enum types, and string, and we can only test for exact equality against constants. We might like to use patterns to test the same variable against a number of possibilities, taking a specific action on each, but since the existing switch does not support that, we end up with a chain of if-else tests such as / prior to Java 21. Static string formatter object obj. String formatted equals unknown, if obj instance of integer I. Formatted equals string.format in %d, I, else if obj instance of long L. Formatted equals string.format long %d, L, else if obj instance of double D. Formatted equals string.format double %f, D, else if obj instance of string S. Formatted equals string.format string %s, S. Return formatted. This code benefits from using pattern instance of expressions, but it is far from perfect. First and foremost, this approach allows coding errors to remain hidden because we have used an overly general control construct. The intent is to assign something to formatted in each arm of the if-else chain, but there is nothing that enables the compiler to identify and enforce this invariant. If some then block, perhaps one that is executed rarely, does not assign to formatted, we have a bug. Declaring formatted as a blank local would at least enlist the compiler's definite assignment analysis in this effort, but developers do not always write such declarations. In addition, the above code is not optimizable. Absent compiler heroics, it will have O(n) time complexity, even though the underlying problem is often O(1). But switch is a perfect match for pattern matching. If we extend switch statements and expressions to work on any type, and allow case labels with patterns rather than just constants, then we can rewrite the above code more clearly and reliably. // as of Java 21. Static string formatter pattern switch object obj. Return switch, obj. Case integer I, greater than string dot format int %d, I, case long L, greater than string dot format long %d, L, case double D, greater than string dot format double %f, D, case string S, greater than string dot format string %s, S, default, greater than obj.to, string. The semantics of this switch are clear. A case label with a pattern applies if the value of the selector expression obj matches the pattern. We have shown a switch expression for brevity but could instead have shown a switch statement. The switch block, including the case labels, would be unchanged. The intent of this code is clearer because we are using the right control construct. We are saying, the parameter obj matches at most one of the following conditions, figure it out and evaluate the corresponding arm. As a bonus, it is more optimizable. In this case we are more likely to be able to perform the dispatch in O1 time. Switches and null. Traditionally, switch statements and expressions throw null pointer exception if the selector expression evaluates to null, so testing for null must be done outside of the switch. // prior to Java 21. Static void test foo bar old string s. If s equals null. System.out.println oops, return. Switch, s, case foo, bar, greater than system.out.println great, default, greater than system.out.println OK. This was reasonable when switch supported only a few reference types. However, if switch allows a selector expression of any reference type, and case labels can have type patterns, then the standalone null test feels like an arbitrary distinction which invites needless boilerplate and opportunities for error. It would be better to integrate the null test into the switch by allowing a new null case label. // as of Java 21. Static void test foo bar new string s. Switch, s, case null, greater than system.out.println oops, case foo, bar, greater than system.out.println great, default, greater than system.out.println OK. The behavior of the switch when the value of the selector expression is null is always determined by its case labels. With a case null, the switch executes the code associated with that label. Without a case null, the switch throws null pointer exception, just as before. To maintain backward compatibility with the current semantics of switch, the default label does not match a null selector. Case refinement. In contrast to case labels with constants, a pattern case label can apply to many values. This can often lead to conditional code on the right-hand side of a switch rule. For example, consider the following code. // as of Java 21. Static void test string old string response. Switch, response, case null, greater than, case string s, greater than, if, s. Equals ignore case yes, system.out.println you got it, else if, s. Equals ignore case no, system.out.println shame, else. System.out.println sorry? The problem here is that using a single pattern to discriminate among cases does not scale beyond a single condition. We would prefer to write multiple patterns, but we then need some way to express a refinement to a pattern. We therefore allow when clauses in switch blocks to specify guards to pattern case labels, for example, case string s when s. Equals ignore case yes. We refer to such a case label as a guarded case label, and to the Boolean expression as the guard. With this approach, we can rewrite the above code using guards. // as of Java 21. Static void test string new string response. Switch, response, case null, greater than, case string s. When s. Equals ignore case yes, greater than, system.out.println you got it. Case string s. When s. Equals ignore case no, greater than, system.out.println shame. Case string s, greater than, system.out.println sorry. This leads to a more readable style of switch programming where the complexity of the test appears on the left of a switch rule, and the logic that applies if that test is satisfied is on the right of a switch rule. We can further enhance this example with extra rules for other known constant strings. // as of Java 21. Static void test string enhanced string response switch response case null greater than case y greater than system.out.println you got it. Case n greater than system.out.println shame. Case string s. When s dot equals ignore case yes greater than system.out.println you got it. Case string s. When s dot equals ignore case no greater than system.out.println shame. Case string s greater than system.out.println sorry. These examples shows how case constants, case patterns, and the null label combine to showcase the new power of switch programming. We can simplify complicated conditional logic that was formerly mixed with business logic into a readable, sequential list of switch labels with the business logic to the right of the switch rules. Switches and enum constants. The use of enum constants in case labels is, at present, highly constrained. The selector expression of the switch must be of the enum type, and the labels must be simple names of the enum's constants. For example, / prior to Java 21. Public enum suit, clubs, diamonds, hearts, spades. Static void test for heart suit s. Switch, s, case hearts, greater than system.out.println it's a heart, default, greater than system.out.println some other suit. Even after adding pattern labels, this constraint leads to unnecessarily verbose code. For example, / as of Java 21. Sealed interface card classification permits suit, tarot, public enum suit implements card classification, clubs, diamonds, hearts, spades, final class tarot implements card classification. Static void exhaustive switch without enum support card classification C. Switch, C. Case suit s when s equals suit.clubs, greater than, system.out.println its clubs. Case suit s when s equals suit.diamonds, greater than, system.out.println its diamonds. Case suit s when s equals suit.hearts, greater than, system.out.println its hearts. Case suit s, greater than, system.out.println its spades. Case tarot t, greater than, system.out.println it's a tarot. This code would be more readable if we could have a separate case for each enum constant rather than lots of guarded patterns. We therefore relax the requirement that the selector expression be of the enum type and we allow case constants to use qualified names of enum constants. This allows the above code to be rewritten as / as of Java 21. Static void exhaustive switch with better enum support card classification C. Switch, C, case suit.clubs, greater than, system.out.println its clubs. Case suit.diamonds, greater than, system.out.println its diamonds. Case suit.hearts, greater than, system.out.println its hearts. Case suit.spades, greater than, system.out.println its spades. Case tarot t, greater than, system.out.println it's a tarot. Now we have a direct case for each enum constant without using guarded type patterns, which were previously used simply to work around the present constraint of the type system. Description. We enhance switch statements and expressions in 4 ways. 1. Improve enum constant case labels. 2. Extend case labels to include patterns and null in addition to constants. 3. Broaden the range of types permitted for the selector expressions of both switch statements and switch expressions, along with the required richer analysis of exhaustiveness of switch blocks, and 4. Allow optional when clauses to follow case labels. Improved enum constant case labels. It has long been a requirement that, when switching over an enum type, the only valid case constants were enum constants. But this is a strong requirement that becomes burdensome with the new, richer forms of switch. To maintain compatibility with existing Java code, when switching over an enum type, a case constant can still use the simple name of a constant of the enum type being switched over. For new code, we extend the treatment of enums. First, we allow qualified names of enum constants to appear as case constants. These qualified names can be used when switching over an enum type. Second, we drop the requirement that the selector expression be of an enum type when the name of one of that enum's constants is used as a case constant. In that situation, we require the name to be qualified and its value to be assignment compatible with the type of the selector expression. This aligns the treatment of enum case constants with the numerical case constants. For example, the following two methods are allowed. // as of Java 21. Sealed interface currency permits coin, enum coin implements currency, heads, tails. Static void good enum switch 1 currency C. Switch, C, case coin.heads, greater than, / qualified name of enum constant as a label. System.out.println heads. Case coin.tails, greater than, system.out.println tails. Static void good enum switch 2 coin C. Switch, C, case heads, greater than, system.out.println heads. Case coin.tails, greater than, / unnecessary qualification but allowed. System.out.println tails. The following example is not allowed. / as of Java 21. Static void bad enum switch currency C. Switch, C, case coin.heads, greater than, system.out.println heads. Case tails, greater than, / error, tails must be qualified. System.out.println tails. Default, greater than, system.out.println some currency. Patterns in switch labels. We revised the grammar for switch labels in a switch block to read, compare JLS section 14.11.1. Switch label, case constant, case null, default, case pattern, guard, default. The main enhancement is to introduce a new case label, case P, where P is a pattern. The essence of switch is unchanged, the value of the selector expression is compared to the switch labels, one of the labels is selected, and the code associated with that label is executed or evaluated. The difference now is that for case labels with patterns, the label selected is determined by the result of pattern matching rather than by an equality test. For example, in the following code, the value of obj matches the pattern long L, and the expression associated with the label case long L is evaluated. / as of Java 21. Static void pattern switch test object obj. String formatted equals switch, obj. Case integer I, greater than string.format in %d, I, case long L, greater than string.format long %d, L, case double D, greater than string.format double %f, D, case string S, greater than string.format string %s, S, default, greater than obj.to, string. After a successful pattern match, we often further test the result of the match. This can lead to cumbersome code, such as / as of Java 21. Static void test old object obj, switch, obj, case string S, if, s.length equals 1, else, break. The desired test, that obj is a string of length 1, is unfortunately split between the pattern case label and the following if statement. To address this, we introduce guarded pattern case labels by allowing an optional guard, which is a Boolean expression, to follow the pattern label. This permits the above code to be rewritten so that all the conditional logic is lifted into the switch label. / as of Java 21. Static void test new object obj, switch, obj, case string S when s.length equals 1, greater than case string S, greater than. The first clause matches if obj is both a string and of length 1. The second case matches if obj is a string of any length. Only pattern labels can have guards. For example, it is not valid to write a label with a case constant and a guard, for example, case hello when call, random, Boolean, expression. There are 5 major language design areas to consider when supporting patterns in Switch. 1. Enhanced type checking. 2. Exhaustiveness of Switch expressions and statements. 3. Scope of pattern variable declarations. 4. Dealing with null. 5. Errors. Enhanced type checking. Selector expression typing. Supporting patterns in Switch means that we can relax the restrictions on the type of the selector expression. Currently, the type of the selector expression of a normal switch must be either an integral primitive type, excluding long, the corresponding boxed form, i.e., character, byte, short, or integer, string, or an enum type. We extend this and require that the type of the selector expression be either an integral primitive type, excluding long, or any reference type. For example, in the following pattern switch, the selector expression obj is matched with type patterns involving a class type, an enum type, a record type, and an array type, along with a null case label and a default. / as of Java 21. Record point int I, int j, enum color, red, green, blue. Static void type tester object obj. Switch, obj. Case null, greater than system.out.println null, case string s, greater than system.out.println string, case color c, greater than system.out.println color, plus c.toString, case point p, greater than system.out.println record class, plus p.toString, case int, yar, greater than system.out.println array of ints of length plus yar.length, default, greater than system.out.println something else. Every case label in the switch block must be compatible with the selector expression. For a case label with a pattern, known as a pattern label, we use the existing notion of compatibility of an expression with a pattern, JLS section 14.30.1. Dominance of case labels. Supporting pattern case labels means that for a given value of the selector expression it is now possible for more than one case label to apply, whereas previously at most one case label could apply. For example, if the selector expression evaluates to a string, then both the case labels case string s and case char sequence cs would apply. The first issue to resolve is deciding exactly which label should apply in this circumstance. Rather than attempt a complicated best fit approach, we adopt a simpler semantics. The first case label appearing in a switch block that applies to a value is chosen. / as of Java 21. Static void first object obj. Switch, obj. Case string s, greater than system.out.println a string, plus s, case char sequence cs, greater than system.out.println a sequence of length plus cs.length, default, greater than, break. In this example, if the value of obj is of type string, then the first case label will apply. If it is of type char sequence but not of type string, then the second pattern label will apply. But what happens if we swap the order of these two case labels? / as of Java 21. Static void error object obj. Switch, obj. Case char sequence cs, greater than system.out.println a sequence of length plus cs.length, case string s, greater than / error, pattern is dominated by previous pattern. System.out.println a string, plus s, default, greater than, break. Now if the value of obj is of type string, the char sequence case label applies, since it appears first in the switch block. The string case label is unreachable in the sense that there is no value of the selector expression that would cause it to be chosen. By analogy to unreachable code, this is treated as a programmer error and results in a compile time error. More precisely, we say that the first case label case char sequence cs dominates the second case label case string s because every value that matches the pattern string s also matches the pattern char sequence cs, but not vice versa. This is because the type of the second pattern, string, is a subtype of the type of the first pattern, char, sequence. An unguarded pattern case label dominates a guarded pattern case label that has the same pattern. For example, the unguarded pattern case label case string s dominates the guarded pattern case label case string s when s.length greater than 0, since every value that matches the case label case string s when s.length greater than 0 must match the case label case string s. A guarded pattern case label dominates another pattern case label, guarded or unguarded, only when both the former's pattern dominates the latter's pattern and when its guard is a constant expression of value true. For example, the guarded pattern case label case string S when true dominates the pattern case label case string S. We do not analyze the guarding expression any further in order to determine more precisely which values match the pattern label, a problem which is undecidable in general. A pattern case label can dominate a constant case label. For example, the pattern case label case integer I dominates the constant case label case 42, and the pattern case label case EE dominates the constant case label case A when A is a member of enum class type E. A guarded pattern case label dominates a constant case label if the same pattern case label without the guard does. In other words, we do not check the guard, since this is undecidable in general. For example, the pattern case label case string S when s.length greater than 1 dominates the constant case label case hello, as expected, but case integer I when I equals 0 dominates the case label case 0. All of this suggests a simple, predictable, and readable ordering of case labels in which the constant case labels should appear before the guarded pattern case labels, and those should appear before the unguarded pattern case labels. / as of Java 21. Integer I equals, switch, I, case -1, 1, greater than / special cases. Case integer j when j greater than 0, greater than / positive integer cases. Case integer j, greater than / all the remaining integers. The compiler checks all case labels. It is a compile time error for a case label in a switch block to be dominated by any preceding case label in that switch block. This dominance requirement ensures that if a switch block contains only type pattern case labels, they will appear in subtype order. The notion of dominance is analogous to conditions on the catch clauses of a try statement, where it is an error if a catch clause that catches an exception class E is preceded by a catch clause that can catch E or a superclass of E, JLS section 11.2.3. Logically, the preceding catch clause dominates the subsequent catch clause. It is also a compile time error for a switch block of a switch expression or switch statement to have more than one match-all switch label. The match-all labels are default and pattern case labels where the pattern unconditionally matches the selector expression. For example, the type pattern string S unconditionally matches a selector expression of type string, and the type pattern object O unconditionally matches a selector expression of any reference type. / as of Java 21. Static void match all string S, switches, case string T, system.out.println T, break, default, system.out.println something else, / error, dominated. Static void match all to string S, switches, case object O, system.out.println an object, break, default, system.out.println something else, / error, dominated. Exhaustiveness of switch expressions and statements. Type coverage. A switch expression requires that all possible values of the selector expression be handled in the switch block, in other words, it must be exhaustive. This maintains the property that successful evaluation of a switch expression always yields a value. For normal switch expressions, this property is enforced by a straightforward set of extra conditions on the switch block. For pattern switch expressions and statements, we achieve this by defining a notion of type coverage of switch labels in a switch block. The type coverage of all the switch labels in the switch block is then combined to determine if the switch block exhausts all the possibilities of the selector expression. Consider this erroneous pattern switch expression. / as of Java 21. Static int coverage object obj. Return switch obj. / error, not exhaustive. Case string S, greater than s.length. The switch block has only one switch label, case string S. This matches any value of obj whose type is a subtype of string. We therefore say that the type coverage of this switch label is every subtype of string. This pattern switch expression is not exhaustive because the type coverage of its switch block, all subtypes of string, does not include the type of the selector expression, object. Consider this still erroneous. Example. / as of Java 21. Static int coverage object obj. Return switch, obj. / error, still not exhaustive. Case string s, greater than s.length, case integer I, greater than I. The type coverage of this switch block is the union of the coverage of its two switch labels. In other words, the type coverage is the set of all subtypes of string and the set of all subtypes of integer. But, again, the type coverage still does not include the type of the selector expression, so this pattern switch expression is also not exhaustive and causes a compile time error. The type coverage of a default label is every type, so this example is, at last, legal. / as of Java 21. Static int coverage object obj. Return switch, obj. Case string s, greater than s.length, case integer I, greater than I, default, greater than 0. Exhaustiveness in practice. The notion of type coverage already exists in non-pattern switch expressions. For example, / as of Java 20. Enum color, red, yellow, green, int num letters equals switch, color, / error, not exhaustive. Case red, greater than 3, case green, greater than 5. This switch expression over an enum class is not exhaustive because the anticipated input yellow is not covered. As expected, adding a case label to handle the yellow enum constant is sufficient to make the switch exhaustive. / as of Java 20. Int num letters equals switch, color, / exhaustive. Case red, greater than 3, case green, greater than 5, case yellow, greater than 6. That a switch written this way is exhaustive has two important benefits. First, it would be cumbersome to have to write a default clause, which probably just throws an exception, since we have already handled all the cases. Int num letters equals switch, color, case red, greater than 3, case green, greater than 5, case yellow, greater than 6, default, greater than throw new arg. This is irritating exception color.to, string. Manually writing a default clause in this situation is not only irritating but actually pernicious, since the compiler can do a better job of checking exhaustiveness without one. The same is true of any other match-all clause such as default, case null, default, or an unconditional type pattern. If we omit the default clause, then we will discover at compile time if we have forgotten a case label, rather than finding out at runtime, and maybe not even then. More importantly, what happens if someone later adds another constant to the color enum? If we have an explicit match-all clause, then we will only discover the new constant value if it shows up at runtime. But if we code the switch to cover all the constants known at compile time, and omit the match-all clause, then we will find out about this change the next time we recompile the class containing the switch. A match-all clause risks sweeping exhaustiveness errors under the rug. In conclusion, an exhaustive switch without a match-all clause is better than an exhaustive switch with one, when possible. Looking to runtime, what happens if a new color constant is added, and the class containing the switch is not recompiled? There is a risk that the new constant will be exposed to our switch. Because this risk is always present with enums, if an exhaustive enum switch does not have a match-all clause, then the compiler will synthesize a default clause that throws an exception. This guarantees that the switch cannot complete normally without selecting one of the clauses. The notion of exhaustiveness is designed to strike a balance between covering all reasonable cases while not forcing you to write possibly many rare corner cases that will pollute or even dominate your code for little actual value. Put another way, exhaustiveness is a compile-time approximation of true runtime exhaustiveness. Exhaustiveness and sealed classes. If the type of the selector expression is a sealed class, JEP 409, then the type coverage check can take into account the permits clause of the sealed class to determine whether a switch block is exhaustive. This can sometimes remove the need for a default clause, which as argued above is good practice. Consider the following example of a sealed interface S with three permitted subclasses A, B, and C. / as of Java 21. Sealed interface S permits A, B, C, final class A implements S, final class B implements S, record C int I,
implements s, / implicitly final.
Static int test sealed exhaustive SS. Return switch, S, case AA, greater than 1, case BB, greater than 2, case CC, greater than 3.
The compiler can determine that the type coverage of the switch block is the types A, B, and C since the type of the selector expression, S, is a sealed interface whose permitted subclasses are exactly A, B, and C. This switch block is exhaustive.
As a result, no default label is needed. Some extra care is needed when a permitted direct subclass only implements a specific parameterization of a generic, sealed superclass. For example, / as of Java 21.
Sealed interface I less than T permits A, B, final class A less than X implements I less than string, final class B less than Y implements I less than Y.
Static int test generic sealed exhaustive I less than integer I. Return switch, I, / exhaustive as no A case possible. Case B less than integer by, greater than 42. The only permitted subclasses of I are A and B, but the compiler can detect that the switch block need only cover the class B to be exhaustive since the selector expression is of type I less than integer and no parameterization A is a subtype of I less than integer. Again, the notion of exhaustiveness is an approximation. Because of separate compilation, it is possible for a novel implementation of the interface I to show up at runtime, so the compiler will in this case insert a synthetic default clause that throws. The notion of exhaustiveness is made more complicated by record patterns, JEP 440, since record patterns can be nested. Accordingly, the notion of exhaustiveness must reflect this potentially recursive structure. Exhaustiveness and compatibility. The requirement of exhaustiveness applies to both pattern switch expressions and pattern switch statements. To ensure backward compatibility, all existing switch statements will compile unchanged. But if a switch statement uses any of the switch enhancements described in this JEP, then the compiler will check that it is exhaustive. Future compilers of the Java language may emit warnings for legacy switch statements that are not exhaustive. More precisely, exhaustiveness is required of any switch statement that uses pattern or null labels or whose selector expression is not one of the legacy types, char, byte, short, int, character, byte, short, integer, string, or an enum type. For example, / as of Java 21.
Sealed interface S permits A, B, C, final class A implements S, final class B implements S, record C int I, implements S, / implicitly final.
Static void switch statement exhaustive SS, switch, S, / error, not exhaustive, / missing clause for permitted class B. Case AA, system.out.println A, break, case CC, system.out.println C, break. Scope of pattern variable declarations. Pattern variables, JEP 394, are local variables that are declared by patterns. Pattern variable declarations are unusual in that their scope is flow sensitive. As a recap, consider the following example, where the type pattern string S declares the pattern variable S. / as of Java 21. Static void test flow scoping object obj. If obj instance of string S and s.length greater than 3, system.out.printlns, else system.out.println not a string. The declaration of S is in scope in the parts of the code where the pattern variable S will have been initialized. In this example, that is in the right-hand operand of the AND expression and in the then block. However, S is not in scope in the else block. In order for control to transfer to the else block, the pattern match must fail, in which case the pattern variable will not have been initialized. We extend this flow-sensitive notion of scope for pattern variable declarations to encompass pattern declarations occurring in case labels with 3 new rules. 1. The scope of a pattern variable declaration which occurs in the pattern of a guarded case label includes the guard, i.e., the when expression. 2. The scope of a pattern variable declaration which occurs in a case label of a switch rule includes the expression, block, or throw statement that appears to the right of the arrow. 3. The scope of a pattern variable declaration which occurs in a case label of a switch-labeled statement group includes the block statements of the statement group. Falling through a case label that declares a pattern variable is forbidden. This example shows the first rule in action. // as of Java 21. Static void test scope 1 object obj. Switch, obj. Case character C. When c.char value equals 7, system.out.println ding, break, default, break. The scope of the declaration of the pattern variable C includes the guard, i.e., the expression c.char value equals 7. This variant shows the second rule in action. // as of Java 21. Static void test scope 2 object obj. Switch, obj. Case character C, greater than, if, c.char value equals 7. System.out.println ding. System.out.println character. Case integer I, greater than throw new illegal state exception invalid integer argument, plus I.int value, default, greater than, break. Here the scope of the declaration of the pattern variable C is the block to the right of the first arrow. The scope of the declaration of the pattern variable I is the throw statement to the right of the second arrow. The third rule is more complicated. Let us first consider an example where there is only one case label for a switch-labeled statement group. // as of Java 21. Static void test scope 3 object obj. Switch, obj. Case character C, if, c.char value equals 7. System.out.print ding. If, c.char value equals 9. System.out.print tab. System.out.println character, default, system.out.println. The scope of the declaration of the pattern variable C includes all the statements of the statement group, namely the two if statements and the println statement. The scope does not include the statements of the default statement group, even though the execution of the first statement group can fall through the default switch label and execute these statements. We forbid the possibility of falling through a case label that declares a pattern variable. Consider this erroneous example. // as of Java 21. Static void test scope error object obj. Switch, obj. Case character C, if, c.char value equals 7. System.out.print ding. If, c.char value equals 9. System.out.print tab. System.out.println character, case integer I, / compile time error. System.out.println an integer plus I, default, break. If this were allowed and the value of obj were a character, then execution of the switch block could fall through the second statement group, after case integer I, where the pattern variable I would not have been initialized. Allowing execution to fall through a case label that declares a pattern variable is therefore a compile time error. This is why a switch label consisting of multiple pattern labels, for example case character C, case integer I, is not permitted. Similar reasoning applies to the prohibition of multiple patterns within a single case label. Neither case character C, integer I, nor case character C, integer I, greater than is allowed. If such case labels were allowed, then both C and I would be in scope after the colon or arrow, yet only one of them would have been initialized depending on whether the value of obj was a character or an integer. On the other hand, falling through a label that does not declare a pattern variable is safe, as this example shows. // as of Java 21. Void test scope 4 object obj. Switch, obj. Case string S, system.out.println a string, plus S, // S in scope here. Default, system.out.println done, // S not in scope here. Dealing with null. Traditionally, a switch throws null pointer exception if the selector expression evaluates to null. This is well understood behavior and we do not propose to change it for any existing switch code. There are, however, reasonable and non-exception raising semantics for pattern matching and null values, so in pattern switch blocks we can treat null in a more regular fashion whilst remaining compatible with existing switch semantics. First, we introduce a new null case label. We then lift the blanket rule that a switch immediately throws null pointer exception if the value of the selector expression is null. Instead, we inspect the case labels to determine the behavior of a switch. 1. If the selector expression evaluates to null, then any null case label is said to match. If there is no such label associated with the switch block, then the switch throws null pointer exception, as before. 2. If the selector expression evaluates to a non-null value, then we select a matching case label, as normal. If no case label matches, then any default label is considered to match. For example, given the declaration below, evaluating null match null will print null. Rather than throw null pointer exception. / as of Java 21. Static void null match object obj. Switch obj. Case null greater than system.out.println null, case string s, greater than system.out.println string, default, greater than system.out.println something else. A switch block without a case null label is treated as if it has a case null rule whose body throws null pointer exception. In other words, this code / as of Java 21. Static void null match to object obj. Switch obj. Case string s, greater than system.out.println string, plus s, case integer I, greater than system.out.println integer, default, greater than system.out.println default, is equivalent to / as of Java 21. Static void null match to object obj. Switch obj. Case null, greater than throw new null pointer exception, case string s, greater than system.out.println string, plus s, case integer I, greater than system.out.println integer, default, greater than system.out.println default. In both examples, evaluating null match null will cause null pointer exception to be thrown. We preserve the intuition from the existing switch construct that performing a switch over null is an exceptional thing to do. The difference in a pattern switch is that you can directly handle this case inside the switch. If you see a null label in a switch block, then that label will match a null value. If you do not see a null label in a switch block, then switching over a null value will throw null pointer exception, as before. The treatment of null values in switch blocks is thus regularized. It is meaningful, and not uncommon, to want to combine a null case with a default. To that end, we allow null case labels to have an optional default, for example, / as of Java 21. Object obj equals switch obj, case null, default, greater than system.out.println the rest, including null. The value of obj matches this label if either it is the null reference value, or none of the other case labels match. It is a compile time error for a switch block to have both a null case label with a default and a default label. Errors. Pattern matching can complete abruptly. For example, when matching a value against a record pattern, the record's accessor method can complete abruptly. In this case, pattern matching is defined to complete abruptly by throwing a match exception. If such a pattern appears as a label in a switch, then the switch will also complete abruptly by throwing a match exception. If a case pattern has a guard, and evaluating the guard completes abruptly, then the switch completes abruptly for the same reason. If no label in a pattern switch matches the value of the selector expression, then the switch completes abruptly by throwing a match exception, since pattern switches must be exhaustive. For example, / as of Java 21. Record int I, public int I, / bad, but legal, accessor method for I. Return I, 0. Static void example an rr, switch r, case avar I, system.out.println I. The invocation example an newer 42 causes a match exception to be thrown. A record accessor method which always throws an exception is highly irregular, and an exhaustive pattern switch which throws a match exception is highly unusual. By contrast, / as of Java 21. Static void example object obj, switch obj, case rr when ri 0 == 1, system.out.println it's an r, default, break. The invocation example newer 42 causes an arithmetic exception to be thrown. To align with pattern switch semantics, switch expressions over enum classes now throw match exception rather than incompatible class change error when no switch label applies at runtime. This is a minor incompatible change to the language. An exhaustive switch over an enum fails to match only if the enum class is changed after the switch has been compiled, which is highly unusual. Future work. 1. At the moment, pattern switch does not support the primitive types Boolean, long, float, and double. Allowing these primitive types would also mean allowing them in instance of expressions, and aligning primitive type patterns with reference type patterns, which would require considerable additional work. This is left for a possible future JEP. 2. We expect that, in the future, general classes will be able to declare deconstruction patterns to specify how they can be matched against. Such deconstruction patterns can be used with a pattern switch to yield very succinct code. For example, if we have a hierarchy of expr with subtypes for int expr, containing a single int, add expr and mul expr, containing two exps, and neg expr, containing a single expr, we can match against an expr and act on the specific subtypes all in one step. // some future Java. Int eval expr return switch, n, case int exprint I, greater than I, case neg expr greater than eval n, case add expr left, expr right, greater than eval left plus eval right, case mul expr left, expr right, greater than eval left eval right, default, greater than throw new illegal. State, exception. Without such pattern matching, expressing ad hoc polymorphic calculations like this requires using the cumbersome visitor pattern. Pattern matching is generally more transparent and straightforward. 3. It may also be useful to add and/or patterns, to allow more expressivity for case labels with patterns. Alternatives. 1. Rather than support pattern switch, we could instead define a type switch that just supports switching on the type of the selector expression. This feature is simpler to specify and implement but considerably less expressive. 2.
There are many other syntactic options for guarded pattern labels, such as p-where e, pfe, or even p&e.
3. An alternative to guarded pattern labels is to support guarded patterns directly as a special pattern form, for example, p&e. Having experimented with this in earlier previews, the resulting ambiguity with Boolean expressions led us to prefer guarded case labels over guarded patterns. Dependencies. This JEP builds on pattern matching for instance of JEP 394, delivered in JDK 16, and also the enhancements offered by switch expressions, JEP 361. It has co-evolved with record patterns, JEP 440.